Will AI help us find alien life? Let's talk about it. In April 2025, a team of astronomers said something almost nobody expected to hear in our lifetimes. They might have found the best evidence yet for alien life. Not a signal, not a photo. A gas floating in the atmosphere of a planet 124 light years away, that on Earth is made by exactly one thing: life. Headlines went out within hours. And within months, that same evidence had quietly fallen apart. This video isn't really about whether the planet has aliens on it. It's about something more useful: how confident something can sound right before it turns out to be wrong. Here's the part almost nobody's talking about. The reason it fell apart is about to happen again. Except this time, it won't be a team of scientists arguing about the data for months. It'll be a machine deciding in an instant and telling us it's sure. This is the story of a signal that convinced the world we might not be alone, and the reason the next signal might be even harder to trust. So I ask again, will AI help us find alien life? Stick around for a story that might help us answer that very question. Meet K2-18b, a planet 2.5 times the width of Earth, orbiting a small red dwarf star 124 light-years from here in the constellation Leo. It's what astronomers call a sub-Neptune, but K2-18b has a nickname that gets people's attention: a Hycean world. Hydrogen atmosphere, possible ocean underneath, sitting right in the star's habitable zone. In 2023, the James Webb Space Telescope took its first real look at that atmosphere and found methane, carbon dioxide, and something else. A faint, tentative hint of a molecule called dimethyl sulfide, DMS. Here on Earth, DMS is made by exactly one process we know of: marine phytoplankton, ocean life, breathing. That first hint in 2023 was too weak to mean much on its own. So in 2025, the same team went back with a different instrument, tuned it to a different slice of infrared light, and looked again. This time, the signal was stronger. Cambridge astronomer Madhusudhan, who led the study, called it a result that ushers in a new era. In statistics, scientists measure how sure they are using something called sigma. This result came in at 3 sigma. That means about a 99.7% chance the signal was real, and roughly a 0.3% chance it was just noise dressed up as a pattern. 99.7% sounds like plenty, but here's the number that matters more. The threshold physicists use before they call something an actual discovery is 5 sigma, 99.99994%. A chance of a fluke measured in 100,000ths of a percent. 3 sigma doesn't clear that bar. It's not nothing, but it's also not proof. Keep that distinction in mind because it's the whole video. Being sure and being right are not the same thing. A smoke detector going off doesn't mean there's a fire. It means the sensor is confident. Whether that confidence is correct is a separate question, and it's the one everyone forgot to ask loudly enough in April 2025. Within weeks, other scientists started pulling the same JWST data apart to check it themselves. 2 independent analyses, one by researcher Jake Taylor and one by a team led by Louis Wellbanks, raised doubts about how statistically solid the original detection actually was. Then, in August 2025, a team led by Kevin Stevenson ran the numbers a different way. Using a different method for handling the mid-infrared data, the exact wavelength range where the DMS signal had shown up. Their conclusion? 87.5% of their preferred retrievals found no evidence of DMS, or its cousin molecule DMDS, at all. Around the same time, a NASA-led team headed by Renya Hu at the Jet Propulsion Laboratory folded in 4 brand new JWST observations and had 3 separate research groups analyze the combined dataset independently. Their finding? The planet really does look water-rich, with a genuine complex atmosphere, but no conclusive evidence of DMS. And that raises an obvious problem. If Webb detected a real signal, how does more data make it disappear? Nobody misread the telescope, and the 2023 and 2025 data aren't in dispute. What moved was how much weight that first reading deserved. The Stevenson team's best explanation was something called red noise, a kind of systematic wobble buried in the mid-infrared data itself, not an actual chemical fingerprint. Different teams, slicing the same noisy data in different ways, ended up seeing different things in it. Same smoke detector, same kind of false alarm, everyone read the sensor correctly, the sensor just wasn't as reliable as its first reading made it sound. Now here's where a completely different experiment released this month makes this a lot more urgent. Christoph Adami has spent over 3 decades studying something most people have never heard of: artificial life. Back in 1993, he helped build a program called Avita, where digital organisms, just self-replicating strings of code, complete, mutate, and evolve inside a computer, the same way real organisms do in the physical world. Adami and his student, Ankit Gupta, set the AI a simple-sounding job. Look at a string of code and decide, is this thing alive or not? In their digital world, alive means one specific thing. The code can copy itself. Dead code can't. So they generated tens of thousands of these digital organisms, some that could self-replicate and some that couldn't. And then they used them to train a neural network to tell the two apart. On that training set, the AI got very good, 99.97% accurate. Show it a piece of code, and it would almost always call alive or dead correctly. That's the number to hold on to, 99.97%, near perfect, on the kind of code it was trained on. Then they went looking for its blind spot. They took one piece of code the AI had confidently correctly labeled dead, can't replicate, not alive, and they started changing it, one tiny instruction at a time. Swap one command, ask the AI again, alive or dead? Swap another, ask again. The code still couldn't copy itself. It was dead the whole way through. But in as few as 150 of those little swaps, the AI flipped. It looked at code that still couldn't replicate and declared with 100% confidence that it was alive. Not probably, certain. And it wasn't a quirk of one starting point. Every sequence they tried, they could eventually fool completely. That's the part worth slowing down on. The code was never alive. Not at step 1, not at step 150. The AI didn't just get it wrong, it got it wrong while insisting with total certainty that it was right. Adami has a name for this whole failure mode. Anything a system wasn't specifically trained on, he calls an out-of-distribution sample. And he says AI's blind spot for that kind of unfamiliar input is close to universal. Stop and notice what just happened. This is the exact same confidence problem from Act 1. The 3 sigma signal that felt like a discovery, just automated, sped up, and handed 100% certainty instead of 99.7. A human team took 2 years and multiple independent papers to responsibly walk back an overconfident reading. An algorithm can produce one with total conviction in the time it takes to run a query. You need an independent way of checking their work, Adami said. There needs to be a human in the loop. So let's put the two stories back together, because separately they're each interesting, and together they're the actual point. K2-18b is, right now, the best real-world case study we have of how a legitimate, career scientist-vetted biosignature claim can climb all the way to 3 sigma and still turn out to be an artifact of the instrument, not the atmosphere. And that took dozens of trained astronomers, multiple independent teams, and the better part of 2 years to sort out properly. The next generation of life-hunting missions won't have that luxury. NASA's Habitable Worlds Observatory, aimed at directly imaging habitable zone planets sometime in the 2040s, will generate more spectra than any team of humans could manually cross-check. Mars sample return missions and any future probes sent into the plumes of Europa will face the same bottleneck: too much data, not enough scientist hours, and a growing temptation to let AI make the first call, or the only call. Adami and Gupta have already planned their next step. They've said they plan to move this exact experiment out of the AVITA simulation and into real-world data to see whether the same 100% confident, 100% wrong failure mode survives contact with Messier, real measurements. That result isn't in yet, but when it lands, it'll either make the problem look smaller or it'll make it look a great deal bigger. Here's the part worth sitting with. None of this means artificial intelligence has no place in the search for life. It means the job has to change. Not final verdict, first flag. A tool that narrows a mountain of data down to the handful of readings worth a human actually looking at twice. The same way Madhusudhan's team looked twice at K2-18b, and the same way Stevenson's team looked a third time after that. Because a smoke detector that never gets tested against the possibility that it's wrong isn't a safety feature. It's just a very confident noise. Every source and paper for this video, including the actual AVITA study and the K2-18b reanalyses, are linked below. If you want more of the real story behind the space headlines, that's exactly what this channel is for. Subscribe if you're in. Here's the question I'd genuinely like your answer to. If a future Mars and Europa mission's AI reported life detected with 99% confidence, would you trust that call or hold out for a human to double check it first? Tell me which and why in the comments. Also, I have a special second question for those of us who work in corporate offices that are pushing AI. Based on your personal experience with AI, would you trust an AI that reports life detected? This has been Apillion. Thanks for watching.